Welcome to class. In the last video, we talked about what differential equations are, so if you haven't seen those, I'd recommend you go back and watch them first. In this video, though, we just spent all this time talking about what differential equations are, but I didn't say anything about, well, if it's an equation, what are its solutions? Let's take a look. Before I actually get to answer that question, I need to share a little bit of notation with you first. When I write f is in Cn of I, really what I mean is that the first n derivatives of f exist and are continuous, hence the C, on the interval I. The way we might read this is that f is n times continuously differentiable on I. So, now we can say that any Cn function is a solution to an nth order ODE if it reduces the equation to an identity on I. Now there's a lot of subtlety in this definition that I'll get to in a second, but before I get to that, I want to drive the key point home. So let's look at an example. And let's look at the ODE, d squared y dx squared minus 2 over x squared y equals 0. And the function phi of x is x squared minus x to the negative 1. Notice that if I take the second derivative of phi, I get phi double prime is, well, let's start with phi prime, shall we? I get 2x plus 1 over x squared, or x to the negative 2. And then I get phi double prime of x, 2 minus 2 over x cubed. So now when I plug these back into the equation, think of y as phi of x. Well, I get the second derivative of phi with respect to x. That is what we just found to be 2 minus 2 over x cubed minus, and now I've got 2 over x squared times y, which is phi. Right? So if I multiply that negative 2 over x squared through, I'll get negative 2 in the first term, and then I'll get positive 2 over x cubed. And what do you know? That's 0. So in this case, I didn't worry about I here. N for this problem, of course, would be 2. As we learned in the last section, this is a second order equation, and we require our function phi to be at least that many times continuously differentiable. When I plugged in this function, do you notice I got something that is identically true, that this interval can be anything that doesn't include 0. Why not 0? Because my solution will become undefined at 0. So it wouldn't make sense to say that this thing that doesn't exist is a solution to the equation there. So I could write a lot of things as an interval I. But for simplicity, why don't I just write all real numbers except for 0? Now, truthfully, when I first gave you the definition of a solution, I undermined the importance of this interval I, which for our class I will be calling the interval of existence. You may also hear this called the interval of admission for that solution. So the interval of existence is just as much a part of the solution as the equation phi of x in this example is. Let me show you an example where it is very important to consider the interval of existence. This time, let's look at dy dx equals 3x squared over 2y. And this time, I am claiming that there is an implicit solution, y squared minus x cubed plus 8 equals 0. Remember, our solution at the end of the day is a function, and I can define that explicitly, meaning I have independent variable equals all of these, dependent variable equals all of these independent variables, but I may define it implicitly here. Do you notice I'll run into a little bit of trouble or weirdness if I try to isolate y because I'll get a plus or minus? So it may actually be easier to just leave the expression as is and use implicit differentiation. So let's get a quick reminder of how that process works. Essentially, I just take the derivative of both sides of the equation with respect to x, of course. And here, the x variable is my independent variable, so I have to be careful when I take the derivative of y squared, y being a function of x. Remember, the chain rule tells me I would take the derivative normally, and then multiply by the derivative of y. With respect to x, everything else will follow normally. I get minus 3x squared plus 0 equals 0, and now I can quickly solve for dy dx. And now it should be obvious why this is a solution. Of course, when I plug this in, dy dx, I just found it's 3x squared over 2y, so of course that's equal to 3x squared over 2y. But I mentioned treating the solution implicitly is going to make our derivatives easier, and that's still true. However, I still have to respect the domain from the given solution here. And remember, the equation is only half the battle. This interval of existence is the other half of the solution, so we need to find that next. Now, surely this is always going to be the case that dy dx, regardless of which x values I plug in, is going to have this form, but the solution doesn't exist everywhere. It would be irresponsible for us to say that this is just the solution, period. Instead, we should look at the domain of that function. And I'll give you a quick refresher on that as well. I need to solve for y. And in doing so, I get that y is plus or minus the square root of negative 8, excuse me, plus x cubed. And we remember from our algebra class that the radicand, fancy name for the thing inside, should be non-negative, or that x cubed minus 8 should be greater than or equal to 0. Quickly solving for x, I get that x is greater than or equal to 2. So this function that I'm claiming is the solution only exists for x values greater than or equal to 2. That said, the interval of existence is all x greater than or equal to 2. The final answer for this problem, then, would be that y squared minus x cubed plus 8 equals 0 on the interval 2 to infinity is the solution to our differential equation.